Welcome back to Industrial Problem Solving. My name is Dave Roysum. In this module, we begin with my favorite part of the course. That is, the street smart methods that I've often used in the some 1,000 plants that I've worked in. Before we begin, let us ask ourselves, what is the most important trait of a good problem solver? Is it a good attitude? Is it a good education or lots of intelligence? Is it lots of good job experience? Is it hard work? Think about this a minute. Pause the tape if you need. Then let me offer my opinion. While all of those traits could be helpful, it is my experience and opinion that laziness is more important. That is, to get to the answers with the least effort. Your boss might call this efficiency, but that word is ill-defined, overused, and misused. Specifically, I mean the least personal effort rather than least costly. If you can buy an answer, do so. Specifically, I mean least personal effort rather than quickest. If a trial can be more gracefully done at the end of a run, that will be easier and probably worth the wait. Finally, let me note that while the previous traits might be helpful, they aren't necessarily always helpful, especially when taken to excess. For example, an upbeat attitude can become a handicap if it becomes Pollyannish, a pitfall which we will discuss in more detail in a future module. Recall from a previous module, one way to inoculate against excessive optimism is the Dunker diagram, which insists on planning for failure. Similarly, more education is not always better for a given problem. Most problems simply do not require a PhD. And if you had one, you'd probably see the world through the eyes of science, even if science was not the fastest way to get the answer. I have worked for years to undo the damage done by higher education. Also, while some experience is helpful, more experience may not be, especially on new problems. The more experience you have, the more likely you will return to the same answers and the same procedures that you'd gotten last time you looked at that problem. Creative thinking can become more difficult as we age because we rely on past analysis and past solutions rather than struggle to look at something from a new perspective. Finally, as I've just opined, hard work is not what we want. Instead, laziness should be our goal. Still, everything, including laziness, should be taken in moderation. Let's put a little more detail on the idea of laziness and how it might affect what the design engineer might do versus what the good problem solver might do. The designer should begin with calculations that might size rollers, roller traction, roller alignment to avoid wrinkling, and so on. Then they should verify those calculations via measurement because, as the saying goes, garbage in, garbage out. The last thing a designer might do would be to observe the web or ask the operator about what they've noticed in that area. Now let's see how a problem solver might approach the same challenges: sizing rollers, roller precisions, etc. If you understand web handling, you can merely look at the flatness of the web going over rollers and make a pretty good assessment of whether the rollers are adequately aligned, as one example. I have taught that to every one of my some 5,000 Web 101 students. The reason for this look before you measure is because it is almost always easier. Thus, for a problem solver, measurements are often secondary, merely to verify a working theory you've already developed by easier means. The reason for the measure before you calculate is that it is sometimes easier. Of course, the well-rounded technical person can work the problem in both directions. If, for example, you notice the look of excessive roller misalignment or undersizing of rollers, you might then need to redesign the machine. In the next modules, which are the central part of this course, we are going to cover a dozen different tools and variations of those tools. In this module, we only have enough time remaining to do one tool, the binary search. It is appropriate to begin with this tool because it exemplifies laziness in a very systematic way. Also, it has very wide application and many variations of application. Let's dive in. Quick! I have a number in mind between 0 and 100. I will tell you whether your guess is too high, too low, or right on. What is your first guess? Obviously, your first guess is 50. If I say 50 is too low, then your next guess is 75, and so on. So let's apply the same technique to determining which roller might be marking your web. This is not an academic problem. Many coder operators and printing machine operators are very good at using just such a street-smart tool. The principle is almost identical to guessing a number. You might go to the middle of the machine first and then determine if the web mark is there or not, and so on. I say almost identical because laziness may dictate variations on this purely procedural method as just described. Sometimes you might not exactly divide the remaining solution space in half if, for example, certain places are much easier to see the web than others. On other occasions, such as if you are downstream, you might merely walk upstream, viewing the web as you go. So whether we use a strictly binary approach or a variation all depends again on which is the laziest way to get the answer. Troubleshooting the causes of a rough roll edge can be one of the most challenging problems in web handling. The reason is, as my Web 101 students have learned, is that the roll edge shows us almost everything we did wrong, both on the winder as well as upstream in web handling, converting, and manufacturing. Think of the roll edge as tree rings. It shows us bad seasons by narrow rings, but the specifics of the reason for the bad season are not easy to identify merely by the narrowness of the tree ring. When problems are challenging, such as this, we must be even more careful to be both organized and lazy. My Web 101 students will recall this diagnostic tree and how to use it. We begin by selecting a specific ring, perhaps involving just one layer. Then we divide the solution space into half, or roughly so. by noting that an outsy might be either an offset wrap or a wide wrap. If it is some combination of offset and wide, one will almost always be bigger than the other. We are not allowed to go down to the next branch or to the next layer until we determine which it is. So how do we get the answer of whether the outsy is an offset or a wide layer? We might determine how much of a width or path change is involved by two ways. One is to measure. The other is to observe. If you already had a pair of edge sensor inches in front of the wound roll, the lazy troubleshooter would use that sensor. However, in the much more likely case of not having edge sensors, you would unwind or cut down to the very layer you are studying, which can be done in almost every situation. Before we wind up this module, excuse the pun, I want to conclude with some very important points about troubleshooting trees. Trees are just a variation of the binary search, and as such are the fastest and surest way to get answers and avoid jumping to conclusions. While constructing a tree is a bit of an art and craft, there are several principles that you should know. First, each node should have as few branches as possible, ideally 2 or 3. Second, there must be a test at each node that unambiguously assigns which branch you are on. Hopefully, that test is easy. Finally, the troubleshooter doesn't actually construct the entire tree, only those branches they must traverse to get to the answer. The reason, as you should have already guessed, is laziness. Thank you so very much for joining me in this continuation to the problem-solving process. I hope I've made the case that laziness is a virtue. I hope I've made the case that street-smart methods, such as the binary search, are some of the best ways to be lazy. Stay tuned for a dozen more tools for the lazy.